Hello students, this is Satyajit Raj explaining you Colorimetry and Spectrometry, Unit 3 of Paper 6. Let us discuss the general features of absorption. First point is absorption is highly sensitive and error-free technique. This is a technique to for the analysis of different kinds of compounds which we prepare in laboratory. The next point is it is most suited method for the analysis of metals like aluminium, arsenic, barium, boron, calcium, lead, nickel, potassium, sodium, and selenium, stannum, tellurium, and zinc, and etc. This is the one of the suited method by which we can analyze the metals such as this all the elements. Okay. The next is it is applicable to the aqueous and non-aqueous solutions also. This method is applicable in the aqueous as well as the non-aqueous solutions. The next point is it requires very less time, and it is giving you very uh, exact results. Okay. The next point is in this procedure, the adsorption does not require sample preparation. We don't there is no need of preparing any type of sample. Okay. The next, it requires very little amount of sample because some of the samples are very costly, so a little amount is also enough for the analysis of the compound. Next is it is independent of molecular form of the metal in the in the example. For example, the sodium content of water sample can be determined irrespective of the molecular form. That is halide, sodium halide, that means sodium chloride, sodium sulfate, or sodium hydride, whatever may be the form, it can be identified irrespective of the molecular form. The metal can be identified and analyzed. Transmittance and percentage of transmittance. Transmittance is defined as a ratio of intensity of incident light to the transmitted light. It is also called as transmission, and it is denoted by capital T, and mathematically it is written as transmittance transmittance capital T equal to capital I denoted by I naught. That is here where I is the intensity of transmitted light and I naught is the intensity of incident light. That is here you can see intensity of incident light is higher. That is the red color is darker compared to the light intensity of the transmitted light, because some of the intensity is observed by the sample which is present in this cube. Okay. Some of the intensity is observed by the sample which is present in this cube. So here the transmitted light is having lesser intensity compared to intensity of incident light. Okay. Here now let us discuss about the percentage of transmittance. Suppose if T, that is capital T, transmittance is 100%, that is uh, no sample, means there is a no observance of the sample. So, intensity is not at all observed by the sample. Then the transmittance will be 100%. That is, if the intensity is not at all observed by the sample, then incident intensity of incident light is equal to intensity of transmitted light. Both will be equal. Then the T equal to the transmittance equal to 100%. Then the compound does not get observed. Then the compound does not observe the intensity at the time. Therefore, the amount of energy observed by the incident light can be determined by using the above assumption. We can calculate the percentage of transmittance. That is, here if we are assuming the percentage of transmittance equal to I by I naught into 100%, it gives you the amount of the percentage of transmittance is taking place. Means it gives you how much amount of intensity is observed by the sample. The percentage of intensity observed by the sample can be identified by this formula. Okay. Intensity of transmitted light is inversely proportional to the concentration of the solution and the length of the medium as shown below. You can see here intensity of intensity of transmitted light. The intensity of transmitted light is inversely proportional to the concentration. If the concentration of the sample is higher, then maximum amount of intensity is observed by the sample. So the intensity transmitted will be smaller. Okay. Similarly, if the length of the length of the medium is larger, then the intensity of light observed, intensity of light observed will be maximum. So the intensity of transmitted light decreases. That is saying that intensity of transmitted light, it is inversely proportional to the concentration and length of the medium as shown below. Okay. Here, graphical representation, by using graphical representation, we can explain, that is path length. This is the path length. As the length is increasing, you can see here, as the length is smaller, here the thickness is smaller, path length is smaller, and intensity transmitted will be nearly 100%. As the length is increasing, this length is increasing, what is happening means the intensity is going on decreasing. Okay. Now the next is concentration. How the percentage of transmittance is observed by the it is dependent on the concentration. Now let us discuss about this one. That is, the percentage of transmittance is also inversely proportional to the concentration. That is, if the concentration is smaller, if the concentration here, you can see here, the concentration here is small, very small, concentration is very low. As the concentration is low, the transmittance is higher, but as as the concentration is increasing, you can see here, as the concentration is increasing, this one transmittance, intense percentage of transmittance is going on decreasing. That is, that this can be uh, known by the graphical representation. That is, intensity of incident light is inversely proportional to the concentration and length of the medium. Okay. Now let us discuss about the observance. It is defined as log inverse of transmittance T, capital T. It is also called as extinction or optical density. It is denoted by capital A, and mathematically it is written as observance, that is capital A, equal to log inverse of transmittance, where T is a transmittance. Okay. Now by using the formula log 1 by m is equal to minus log m, by using this formula, we can write here observance A equal to minus log T minus log transmittance. Okay. Now, substituting the value of transmittance, that is capital T equal to I by I naught in the above equation, where in the above equation we get observance equal to minus log I by I naught. Again using the same formula, we will get observance equal to log I naught by I, where observance is equal to log I naught by I. This formula is coming. We are to get this formula. We are using this equation. Okay, one log 1 by m is equal to minus log m. Okay. Now, let us discuss the relationship between observance and concentration of sample and length of the medium. If the intensity of transmitted light is equal to the intensity of incident light, that is, if I is equal to I know intensity of transmitted light, intensity intensity of transmitted light is equal to intensity of incident light, that is I equal to I naught, then observance becomes log I naught by I naught, means it becomes observance equal to log 1, then that is observance is equal to 0, means no observance is occurring. No observance is occurring, means none of the intensity is observed by the sample is not at all observing the intensity of the light, then observance is not at all occurs. When the intensity of transmitted light is equal to the intensity of incident light. Okay. By this, we can observe that intensity is directly proportional to the concentration and length of the medium. That is, here as the concentration of the sample is increasing, what is happening? The sample intensity of the sample light is getting observed. Intensity of the light is getting observed with the sample. Similarly, as the length of the medium is increasing, the maximum intensity of the incident light is observed. Then, less amount of the intensity is observed in the transmitted light. Okay. Now, observability. Observability of a solution is defined as the ratio of observance to the product of concentration and the length of the medium. That is, observance is directly proportional to the length of the medium, that is B, and C, that is concentration. Then A is the proportionality constant. Called as observability. Okay. Now, where is the molar observability? When the concentration in the equation, is expressed in moles per liter and length of the medium B is in centimeters, then proportionality constant is called as molar observability or molar extinction coefficient. It is denoted by epsilon, and the equation is A is directly proportional to epsilon Bc, where B is length of the medium and C is the concentration. Then molar observability equal to A divided by BC, where B is a length of the medium and C is the concentration of the sample. Now, let us discuss about the units of molar absorptivity. That is, here B is in centimeters, length of the medium is in centimeters, and concentration is in moles per liter. Then units of molar absorptivity becomes liters per mole. Lambert's law. Lambert's law is very important topic with respect to your semester exams. Okay, according to Lambert's law, when a beam of light is allowed to pass through a transparent medium, the rate of decrease of intensity with the thickness of the medium is directly proportional to intensity of incident light. That is, rate of decrease in intensity of incident light, rate of decrease of, that is, di by dx with respect to thickness of the medium, rate of decrease in intensity. The minus symbol represent decrease in intensity, rate of decrease in intensity with respect to thickness of the medium is directly proportional to intensity of light I. That implies minus di is equal to ki dx, where this k represents proportionality constant. Okay, now this proportionality constant is also called as adsorption coefficient or extinction coefficient. Now, manipulating the equation in this form, we will be getting di divided by I is equal to minus k dx, minus k dx. We are manipulating this equation in this form, and on integrating this above equation 1 using formulas, integration of 1 by x is equal to dx equal to ln dx ln x, and integration of a constant a dx is equal to ax plus c. Using these two formulas, we'll be getting the equation 1 as ln I minus kx plus c. We are using these two equations for integrating this equation number 1. Okay, we are using the equations these two for integrating the equation number 1, and we are getting the result as ln I is equal to minus kx plus c, where c is a constant. Okay, now when x equal to 0, that is thickness is equal to 0, then it implies in intensity of transmitted light is equal to intensity of incident light. When the thickness is equal to 0, we are not, then when the thickness is equal to 0, what is happening? X equal to I naught, that is intensity of incident light equal to intensity of transmitted light equal to intensity of incident light. Okay, substituting the above value, that is I equal to I naught in the equation 2, that is we are getting ln I minus kx x equal to 0. Then this whole thing becomes 0. This whole things become This whole thing becomes 0. X equal to 0 means this whole thing becomes 0. And ln is equal to ln naught. Ln naught. Okay. Then we are getting the equation as ln, that is ln I minus ln naught minus kx minus ln naught. Okay. Okay. Now the above equation, that is according to the equation ln I minus ln naught is equal to ln I divided by ln naught by using the formula given below. Okay, is equal to minus kx dx, that is the equation 3. Equation number 3, by using the formula, that is here we are using this formula, that is log a m by n equal to log a m minus log a n. By using this formula we are getting the equation number 3. Now by using the formula, that is ln x equal to 2.303 log x, by using this formula the equation number 3 can be converted in the form of 2.303 log x I by I naught is equal to minus kx. That is, in place of ln x, we are keeping 2.303 log. Okay, by using this formula. Okay, by manipulating the equation, this equation, we are getting the equation number 4. We are getting the equation number 4. Now, by using the formula, that is natural logarithm ln x is equal to kx equal to, it represents n equal to e to the power of x. This is the relationship between natural logarithms and exponential form, that is log ln x equal to x, that is represents n equal to e to the power of x. Using this formula for the equation number 3, for the equation number 3 we are getting e to the power of minus kx equal to e to the power of minus kx equal to I by I naught from the equation number 3. Now by it can be manipulated as I equal to I naught e to the power of minus kx. The equation number 3 can be manipulated. The equation, this equation can be manipulated in the form of I equal to I naught e to the power of minus kx. That equation is termed as equation number 5. Now the equation number 5 is known as Lamberts equation. The equation number 5 is known as Lamberts equation, where I is equal is intensity of transmitted light, and I naught is the intensity of incident light. Okay, and where k is the extinction coefficient and x is the distance, x is here the length of the medium. Here it is taken as L, whereas here it is taken as x. Okay, now intensity of incident light observed. Now let us calculate the intensity of light observed is equal to, I naught, that is intensity of incident light, minus intensity of transmitted light. Intensity of transmitted light can be calculated by using formula, by using Lambert's equation. So I is substituted in the equation, in this equation, and we are getting as I observed equal to I naught minus I naught e to the power of minus kx. It can be converted as I equal to, on taking common I naught, we are getting I observed equal to I naught 1 minus e to the power of minus kx. By using this formula, we can calculate the intensity of observed light. Okay. Now let us calculate let us know the relationship between extinction coefficient and absorption coefficient. That is, extinction coefficient k dash of the observing medium is related to absorption coefficient k by the expression k dash equal to k divided by 2.303.